Hello everyone, we're going to review some examples for the pre-calculus Delta Math assignment on limits and continuity. So the first skill that we were going to look at is how to find limits graphically, type 1. Alright, so let's say we have this problem. It says answer all of the questions below about the function f of x graph below when x is equal to -5. So it seems like we have a piecewise function here. There's a bunch of discontinuities. There's a jump. There's a removable. But we're focusing on, right now, when x is equal to -5. So this problem says, what is the limit when x approaches -5? The little minus sign means from the left of f of x. So this is where -5 is. So you trace it with your mouse. As it approaches -5 from the left, it is approaching -2. Even if that was an open circle, the answer is still -2. So let's say we're approaching -5 from the right. So the limit as x approaches -5 from the right, so from the right, it's going left, from the right, it is approaching -5. So because the limit from the left is approaching -2, but the limit from the right as it approaches -5 is going to -5. Therefore, this is a jump discontinuity. Because of that, because the limit from the left and the limit from the right are not the same, the limit as x approaches -5 is what we call undefined. Or more precisely, this is where there is an issue here. These are used kind of interchangeably. The limit doesn't exist, right? So undefined and does not exist are slightly different. Typically, we use undefined for values for points, where a point is not defined there. Does not exist are when we're talking or referring to limits. So the limit does not exist. However, f of -5 at x is equal to -5, we're looking at where the y value is defined. So when x is -5, the y value is at -2. There's a closed circle there. Then we submit our answer. There we go. Just make sure that when we refer to undefined, we're referring to a point. D and E, this stands for does not exist. We're using that to explain that a limit doesn't exist because the limit from the left and the limit from the right do not match, right? So when they do not match, or when they're not equal, they do not exist. When we're talking about point values, so this is something that you have done before, you're valuing the value of x. You're valuing where y is when x is whatever number that is. So you're finding f of -5. We look at our graph. When it's at -5, the y value is clearly defined at -2. If it was an open circle at this particular point, then the answer for this would have been undefined. Let's go back. Let's do the second example. The second skill is on limits of piecewise function. So for the function shown below, determine the limit as x approaches -2, the plus sign means from the right, all right, of f of x. So here we have this graph here. There are two sections. One is when it's approaching -2 from the left side. I noticed because this says x is less than or equal to -2. So that means that this graph is from the left-hand side. If it's greater than that particular value, which in this case we want, it's greater than, because if you imagine a number line, if a function is to imagine a number line on -2, right, from the left, right, they're all values that are to the left of -2. So from the right, or values to the right of negative 2. So on the right side, you're going to get a linear function. We know this because the equation of the line is 2x plus 9, where from the left side, you're going to get a quadratic. So since we're doing this algebraically, we can just ignore this side. We want the limit as x approaches negative 2 from the right. So what you're going to do is you're going to take negative 2, right? And you're going to plug it into this particular equation. So you're going to take 2x plus 9, right? That is our function from the right-hand side. And we're going to evaluate f of negative 2. Now keep in mind that even though there's no equal sign here, we're going to evaluate it at negative 2 for this particular piece, because what it's going to do is it's going to plug in a value where it's undefined, but your limit is still going to that particular point. All right. So let me just repeat myself. This is saying the limit as x approaches negative 2 from the right. It's not asking you to evaluate f of negative 2. However, we're going to evaluate f of negative 2 at this particular point, because what that is going to give us is visually, right? Imagine this is the line, right? It's going to give us this value here. But since that value doesn't exist for this particular function, we're just evaluating it at negative 2 for that piece to get where that point is undefined. All right. So therefore, when we plug in negative 2 into this equation, f of negative 2 would be negative 4 plus 9. So f of negative 2 for this particular piece is 5. All right. So even though I'm writing it as f of negative 2 is equal to 5, this is actually a point, negative 2 comma 5, this point, right? Negative 2 comma 5 does not exist. But that is where the limit is. The limit would be at positive 5. So to demonstrate, this line would have been our graph, right? So as you're approaching that function from the right-hand side, it's going to 5, right? So you're evaluating this function at 5. So when you write this, you need to be careful. The way that I'm writing it, it looks like, oh yeah, you're evaluating f of negative 2. But this is more of a correct way of doing it, of saying, well, you're actually finding the limit as x approaches negative 2 from the right, right? So when you plug in that value, you're going to get 5. But since we're used to using function notation, you just have to be careful, because f of negative 2 for this actual function, you actually have to plug it into the first equation to get f of negative 2, because that point is actually defined. So just be mindful of, like, when you use function notation to evaluate limits. It's kind of weird, so you just need to be careful. You probably want to use the proper notation, which is limit as x approaches negative 2 from the right of f of x is equal to all of this. Then you plug in a negative 2 in here. All right. So the next type of example that we're going to have are types of discontinuity graphically. So the graph of the function f of x is shown below. State all values of f of x in the open interval negative 5, in the open interval negative 9 is less than x, which is less than 9, for which the function has an infinite discontinuity. So the definition of an infinite discontinuity is when the limit as x approaches a value, such as negative 1 from the left, is going to infinity and or negative infinity. And from the right side, it's going to positive infinity and or negative infinity. So either or. So we need to state all values of x. So it happens here at negative 1. let's see like how we input it. So we can actually input it if we have multiple values. We can do pluses to indicate that we have multiple values, because I can foresee that we have multiple answers. So there is an answer here at -1. So at 4, so there's only 2 answers. So at 4, the limit as x approaches 4 from the left is going to positive infinity, and from the right is going down to negative infinity. So there are 2 answers here, right? Sometimes you might have jump discontinuities, sometimes you might have point discontinuity, right? So when it's a jump, just remember that the limit from the left and the limit from the right are not the same. So in this case, here for this example, right, at -6, there is a jump here. So I have a jump. This is not a jump because the limit from the left and the right are the same. So therefore, this is actually a point discontinuity. Same with this one. That's a point. It's a tricky one. Sometimes point discontinuities look like jump, but just remember that jump discontinuities are when the limits are not the same. So at 5, there is a jump here. All right. So the 4th skill is on how to demonstrate continuity from a graph. So here we are using the definition of continuity, which is great, right? Remember that the definition of a continuous function at any given point is that the limit from the left and the limit from the right are the same, right? And the limit from the left and the right is defined, and such that the value f of that value is equal to the y value of the limit. So let me give you an example. Let's say we have this function, and we need to determine whether the function f of x, graph below, is continuous at x is equal to -4. So in this example here, -4. So this problem is not very interesting because you can look at it and it's continuous, but we can still do this example, and then we'll do another example where it's not continuous. So this example is pretty straightforward in the sense that because it's continuous at -4, right? The limit as x approaches -4 from the left, it's going to 1. The limit as x approaches -4 from the right is also going to 1. It can be determined that the limit exists and it's equal to 1 because these two are exactly the same. Therefore, this limit must be 1. Therefore, it can be seen that f of -4 is 1. So this problem is not very interesting because it's continuous here. So we'll answer the last question. Therefore, it can be stated that the function f of x is continuous at f of -4 because the limit from the x, no, that's not true. The limit as x approaches -4 is equal to f of -4. That's correct. We want the limit to be equal to the evaluation of that point at -4. So we submit our answer, and there we have it. So this problem is not very interesting. Let's do a more interesting problem. So let's take a look at this. At x, let's see if it's continuous at -2. All right, so this is a much more interesting problem because at -2, well, there's a discontinuity here. So let's see. Since the limit as x approaches -2 from the left, so we follow this graph from the left, we trace it. So from the left, it is going to 2. The limit as x approaches -2 from the right, it is approaching 7. So as of right now, the limit as x approaches -2 does not exist. And the reason why it does not exist is because f of -2, well, what's wrong here? Okay. So like when you click on does not exist, this other stuff goes away. So the limit does not exist because as you go from the left, it's going to 2. As you're going from the right, the limit from the right, it's going to 7. Because these two are not the same, the limit does not exist, right? Another word is D and E, does not exist. That's how you can drag this somehow. Anywho, furthermore, it can be seen at f of negative 2. Okay, so if we look at negative 2, right, there is no closed circle anywhere. Huh. If there was, you would write down the y value, but because there is no closed circle, right, we have to choose between does not exist or undefined. And as mentioned before, when there is a point that's not there, we call that as undefined. It's an undefined point. Wait, how do we? Odd. So if I click this and press undefined, okay, there we go. That was weird. So you need to click on the box and click on undefined, and it should have it there. I think you can also type it in. Nope, you cannot type it in. Therefore, it can be stated that the function f of x is not continuous at x is equal to negative 2 because we call that a jump discontinuity because the limit from the left and the right are not the same. Because the limit as x approaches negative 2 exists? Nope, that's not true. It does not exist. Or is there another third option? The limit as x approaches negative 2 is equal to f of negative 2. That's not even true at all. It has to be the second one because the limit as x approaches negative 2 does not exist. We could have stopped there to say it's continuous or not, but you also want to talk about, like, even if there was a closed circle, you do want to mention this piece regardless, right? And you probably want to mention somewhere for this problem, right, that this is a jump discontinuity. This is only used to determine continuity, but as a class, we need to determine what kind of discontinuity this is. So this is a jump. Oh, we need to submit our answer. And there we go. All right, the very last one, the very last type of example that we're going to do is how to essentially make a function continuous. So as of right now, in this example, we are given a piecewise function, and we need to make sure that it's continuous. So essentially what these problems are is on a scale, you have some piecewise function. Let's just make it a line. You have another piecewise function. The goal is to make it continuous, meaning you want to somehow drag these limits, right? So that, like, move them up or down, etc., such that I want to move this piece, like for instance, up. So the limit from the right, the limit from the left and the right are the same. And you also want it such that this point is also defined there, right? That's the goal of these, like, problems where it's like find k to make it continuous. So that's the goal behind it geometrically or graphically, but to do it algebraically, essentially what we want to do is say that the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x, right? So remember, the limit from the left, this guy, is when it is less than a value. So in this case, we want to pick the value that are less than. In this case, it's k of kx minus 4. We want kx minus 4 to be equal to, right, the limit as x approaches 2 from the right, which happens to be kx squared. And because we're evaluating it at when x is equal to 2 from the left and from the right, you want it such that the x values are going to be defined at 2, right? You want it to be defined at 2. So what you're going to do is you're going to replace the x's with 2. So therefore, I'm going to replace the x's with 2. Whenever I see an x, I replace it with a 2. So here we have k times 2, which is 2k, minus 4 is equal to 2 squared is 4. So this is 4 times k, which is 4k. So now we have a couple options. We can move all the k's to the left or the right. I personally would like to move the k to the right side because the constant, the number, is already on the left side. So we'll save ourselves an extra step. So to do that, what we need to do is we need to move the 2k to balance it. We need to subtract 2k from both sides. So negative 4 is 4k minus 2k. So negative 4 is equal to 2k. So we get up to this step, and what we want to do is divide both sides by 2. So negative 2 is equal to k. So when we plug in k as negative 2, right, into this particular function, now the two pieces, right, the limit from the left and the limit from the right will be equal to each other. So therefore, k in this case would be negative 2. And there we have it, right? So you want the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right, which also happens to be f of 2, right? And f of 2, when you plug it in, you can actually plug it into either of them if you're curious as to where the y value is. But in this example, we only need to figure out what k is. And that's all we have.